I was going to say, hopefully there won't be any tech issues today. The battery on my Surface tablet is not charging, so at some point it might die, but let's see how long it lasts. Okay, so today we're going to be talking about finding critical points of functions, and in particular finding the maximum and minimum values of a particular function. So why might we care about this? Well, suppose you want to find the hottest or the coldest place on a map. You want to find the maximum or the minima. You might want to work out what the maximum yield is of a crop, depending on the types of nutrients that you supply. And you could supply multiple nutrients. That's why you'd have a function of multiple variables. So there's lots of different cases where we would be interested in trying to understand where a function achieves a maximum or a minimum. Okay, so in the pre-recorded lecture, I talked about quite a lot of vocabulary and terminology related to critical points. Hopefully the general idea of what we're doing here is fairly intuitive though. Okay, so we say that a function has a local maximum if all values nearby have a lower value or lower than or equal to that value. So this one indicated over here on the left-hand side of this diagram is a local maximum because it is the top of this little peak. We have a local minimum if you're at the bottom of a valley, essentially. So all values around that function are, all values around that point of your function are higher, or at least greater than or equal to. So the greater than or equal to matters because you could have a constant function. So we usually picture these as being strictly greater than, but it can be greater than or equal to, or less than or equal to for a critical point. We also have that all, if we have all points in the domain of our function are less than the value that is achieved at a particular point, then that point is an absolute or global maximum, and vice versa. All points in our domain produce a value of our function that is higher than that is achieved at that point, then we have a global or absolute minimum. Okay, so this is just terminology. And we can work out candidates for our critical points, for our maximum minima, all of our critical points, sorry, satisfy our partials being equal to 0, okay? And our maximum and minima, therefore, always have our partials with respect to x, with respect to y, both simultaneously being equal to 0. The reason I started there for a second is because we can have this case in the middle where we can also achieve a saddle point. So at this saddle point here, both of our partials are equal to 0, but in one of the directions, in say the x direction here, I think, yeah, in the x direction, it's acting like a minimum, and in the y direction, it's acting like a maximum. So this is why we call it saddle, because it takes this saddle shape, looks a bit like a Pringle. And so that there is not a local maximum or a local minimum, and we refer to it as a saddle point. Okay, how do we actually calculate these? We can look at the second order partial derivatives of our function, and then we can plug them into this thing here called the discriminant, where we take the product of our second order partials with respect to x and with respect to y, multiply those together, and then we subtract the square of the cross partial derivative, so f sub xy at that point. And if this value d is positive, then we know that we have a local maximum or a minimum. And then the sign of either our f sub xx or f sub yy, it doesn't matter which one, the sign of that at our point tells us whether we have a local minimum or a maximum. If this d is negative, then that means that we don't have a minimum or a maximum. We actually have a saddle point. And if the d is equal to 0, then our test is inconclusive. So we have to do other things. That's not going to be covered in this course, though. So we'd always be, as far as you're concerned in this course, in one of these 3 examples here. Okay, so in the pre-recorded lecture, I stepped through the example of how we do this. So we have a function here, and we want to find the local minima and maxima and classify them, as well as classify any other critical points. So in this case, we also have a saddle point. So we set our partial derivatives equal to 0. We calculate them first, set them equal to 0. And then we work out all of our critical points. There are 5 in this case. And then to classify them, we work out those second order partials, calculate our discriminant, this thing here, and then just substitute in each of those critical points. Okay, so it's just like a recipe that you can follow here. To work out your critical points, first find your partial derivatives, solve those equations when they're equal to 0. That will give you a list of points. Those are your critical points. And then to classify them, look at your second order partial derivatives and calculate the discriminant. Okay, so we can come up with a table like this. Does anyone have any questions about any of that material? Nope. Okay, let's go through some problems then. Okay, so here we've got some level curves describing a function in 2 dimensions. So what we want to do is we want to predict the critical points of f and whether they're likely to be local maxima, local minima, or saddle points. Okay, so how might we do this? Well, if I zoom in a little bit here, we could work this out algebraically, right? We could go through the process that I just talked about, but we can also just look at the level curves in this case. And we can see here that we have point 1 here, this level curve here, which you can't really see, but it's essentially just a dot here. Everything around that, well, if we go in this direction, we're going to 0.9. This direction is also 0.9. So this is 0.9, 0.5, 0, minus 0.5. Likewise, in this direction, we've got 1.1, 1.5, 2, and 3. So we can see here that if we're at this red dot in the center, and we go either down to the left or up to the right, then we're going to be going towards a level curve at 0.9, which is less than 1. And if we go in this direction here, top to left or bottom right, we're heading towards level curves that are increasing, going from 1 to 1.1. So in one direction, or rather in 2 of our 4 directions, if you like, we are decreasing our function value. And in the other 2 of our 4 directions, we're increasing our function value. So this suggests to me here that we've got a saddle point. Okay, let's look at what other potential maxima or minima there are. Well, if we keep moving in this direction, up here, we've gone from 0.9 down to 0.5, 0, minus 0.5. And then eventually, if we keep, ignore that for a second, if we keep going in this direction here, eventually we start increasing again. So we've crossed minus 0.5. If we keep going in this direction here, we're eventually going to go back up to 0.0, 0.5, 0.9, and so on. So that tells me that there should be some minimum value in here. And we can predict, based on how these level curves are set up, that we've got a minimum value here at 1, 1. So we predict that this will be a local minimum. Exactly the same going on in this direction. Our function values are decreasing as we cross those level curves. It suggests that there is also a local minimum, this value here. Okay, so we can just look at our function and say, okay, where do we expect our local minimum and maxima to be? Here we actually have an equation for our function. So we could plug in each of these different values at 0, 0, 1, 1, minus 1, minus 1, and we can work out what those values are. So in this case, we predict that we have local minima at 1, 1, and minus 1, minus 1. We plug these values into our function, f at 1, 1. Well, we're going to have 1 to the 4 plus 1 to the 4 minus 4 times by 1 times by 1 plus 1, which ultimately ends up equaling minus 1. And f at minus 1 minus 1 also turns out to be minus 1 as well. So these are local minima. And this is a good check to do if we have that function there to plug them in, because we can see that all of our other level curves are at minus 0.5 and above. Therefore, these values here at minus 1 are our lowest values. So although it's not written on here, these are local minimum at the value f of 1, 1 is equal to minus 1. And similarly down here, local minimum at f of minus 1 is equal to minus 1. It's a lot of minus 1s. Okay, and then our saddle point. Well, that we thought was at 0, 0. And we can work out our function value there as well, just substituting 0, 0 in. And this just cancels down to 1. Okay. So we can classify what's going on at these critical points in our function by just looking at those level curves. And if we have the function available, we can also plug these values in. We could also potentially estimate those values if we didn't have our function, just by looking at the level curves and how they're distributed. Okay, let's get you guys practicing this by taking this function here. So we have fxy is equal to 3xy minus x cubed minus y cubed. What I want you to do is to find your critical points of this function and then classify them. So before you do that, let's just run through, shout out what are the steps we're going to take. So how do we find our critical points? What's the first thing we do? Find your partial derivatives, great. And then what do you do to, once you find your partial derivatives? Set them to 0, great, and solve them. And then how do you classify your critical points into whether they are minima, maxima, or a saddle point? Second partial derivatives, and then you calculate the discriminant. So f sub xx times by f sub yy minus f sub xy all squared. And then the sign of that and the sign of your f sub xx as well. Okay, so work through that. I'll walk around the class and see if anyone has any questions. Okay. Okay, can I just check who's found the critical points? Show of hands. Okay, the couple. Who's found the partial derivatives first of all? Okay, good. So let's just check everyone's on the same page here. So we have f sub x, the partial with respect to x is going to be 3y minus 3x squared. And the partial with respect to y is going to be 3x minus 3y squared. Is that what everyone got? Good, okay. So our critical points are just when f sub x and f sub y are both equal to 0. You solve these equations simultaneously. So think about f sub x being equal to 0. This gives us, we take the 3 out the front, 3 times by y minus x squared is equal to 0. So the 3, we can just divide 3 by that. So we must end up with y being equal to x squared. Okay. Did everyone get to that point? Yeah, okay. So let's leave that as it is for now. Look at the partial with respect to y. So when this is equal to 0, we get 3 times by x minus y squared is equal to 0, which tells me that x must equal y squared. Did everyone get to that point? Did everyone get stuck at that point? Seeing some nodding. Okay, that's fine. Okay, so what we could do here is we could just substitute, say, this one into this one over here. Okay, so if we square both sides here, we're going to get y squared is equal to x to the 4. And then we can substitute this into this side. So we have a y squared here, and we've got a y squared here. So we can end up with x is equal to x to the 4. We can then factor out, well, take the x to the other side and then factor it out. So we're going to have an x to the 4 minus x is equal to 0, which we can also write as x times by x cubed minus 1 is equal to 0. So this tells me either x must be equal to 0 or x cubed must be equal to 1. So that tells me that x must equal 0 or 1. Because x is either equal to 0 or 1, I can then substitute it back into this equation up here where we had y is equal to x squared. So that tells me that y is equal to 0 or 1. So our points, our critical points are xy is equal to 0, 0 or 1, 1. So if we zoom in on this figure here, these are just colored in level curves, essentially. This is a contour plot. So if we estimate where we are for 0, 0, that should be here, and 1, 1 is somewhere here. And those points kind of make sense, right? That this point here, if these colors are corresponding to the height of our function, so say darker is perhaps a higher function value, the shading goes lighter, and then when we come out of here, it goes darker again. So it suggests that this is probably a local minima, if that's what our shading is indicating. Darker is a higher function value. Here, this might be a saddle point because we're going lighter on this side and lighter on this side, and then slightly darker on this side and slightly darker on this side. So just by inspection here, I can probably guess that this bottom left one is a saddle point and the top right one is a minima or a maxima. Obviously, if you have Wolfram Alpha, you can just plug these things in to check. And as with several of the other examples that we've talked about previously, or things like how do we calculate partial derivatives, you can just come up with your own function, like something like this, whatever you want it to be, as practice, plug it into Wolfram Alpha, and you can you'll be able to visualize where your minima and maxima are whilst you do your own algebraic analysis like this, okay? So we've identified our critical points, 0, 0, and 1, 1. So now we want to classify them. Has anyone managed to classify these yet? Okay, 1 hand, 2 hands. Do you guys want to have a go at classifying them? So just recall that we want to calculate our second order partial derivatives and then substitute those into our discriminant, and then look at the discriminant, evaluate it at each of these critical points. So we've just got 2 critical points here, 0, 0, and 1, 1. So you want to work out f sub xx, f sub yy, f sub xy, and then your discriminant, f sub xx, f sub yy, minus f sub xy squared. Okay, have a go at that. Okay, can someone tell me what f sub xx is? Minus 6x, was that? Okay, f sub yy? Good. And f sub xy? 3. Okay, so you notice in this case, regardless of what our critical point is, f sub xy is always 3. So this is not going to depend on our critical points when we substitute them in, whereas these values here, because there's x's and y's here, those values will depend on our critical point, okay? So if we calculate our d, we could work out it in general case. I'm just going to leave it in that form for now. And actually, no, I'll leave it. I'll calculate it out in full, actually. Yeah. So we've got f sub xx times by f sub yy. So we're going to have minus 6x times by minus 6y. Minus 3 squared, which is just going to give us 36xy minus 9. Or we can factor out the 9, so we have 9 times by 4xy minus 1. You might want to do this step and do the general case, or you might just want to skip straight to calculating these values at your critical points and then creating your d individually. There might be advantages of doing it that way. For example, I think the one in the pre-recorded lecture, we found, for example, that the f sub xy, I think, was always equal to 0 for a set of critical points. Okay, so rather than writing out this potentially big, long, complicated capital D here, you end up being able to eliminate some of the terms. Okay, so it just depends on the functions involved as to which way you want to do it. You could write out the general case like this, or look at them individually. Okay, so what we do now, we just substitute in our critical points. So at 0, 0, d of 0, 0 is equal to, well, let's see. This here is going to be 0. This here is going to be 0. And then we're subtracting this squared. So I don't actually need to bother working out what the value is. I know that we're going to be setting this term here to be 0, and then we've got minus something positive squared. So I know that D is going to be negative. In this case, it happens to be -9, which is negative. So if we go all the way back to the beginning of our classification table here, D is negative. So that tells me that we've got a saddle point at 0, 0. Okay, as simple as that. All we need to do is just substitute those values in and then go back to our table to see what the classification was. So it tells me this is a saddle point. Okay, how about at 1, 1? Well, substitute D of 1, 1. Let's use this formula over here this time. So we're going to have 9 times by 4 times by 1 times by 1 minus 1, which is greater than 0. So 9 times by something positive greater than 0. Again, we don't actually have to worry about what it is. We just need to worry about its sign. And if we look at f sub xx, for example, this is going to be -6 times by 1. So that's just -6, which is negative. Okay, so with these two pieces of information, we can go back to that table again, back at the beginning. So you have D being positive, and or in this case, actually, aren't we? D being positive and f sub xx is negative. So that tells me that we have a local maximum. So the local max at 1, 1. Here we've got a saddle point at 0, 0. You can also work out the function values of those points just for a little bit more completeness. So you can say f at 0, 0 is just going to be equal to 0. So just substituting those into the original equation. And we have a local maximum, so we can find what is the local maximum value of our function by substituting those values in. So f at 1, 1 is just equal to 1. So that's just a little bit of additional completeness there to fully classify what is going on with this function. Okay, does anyone have any questions about how we either find critical points or how we classify them? Yes.
How did you get the f of xy?
F of xy, yep. So here, this is just f sub xy is just the partial with respect to x, and then we take the partial with respect to y. So, and we can actually do that in the other order. For all the functions that you will see, everything that will be covered in this course, f sub xy is equal to f sub yx. So all we do is say, take the partial with respect to x here, and this is just another function now, so 3y minus 3x squared. So if you want to find f sub xy, we just take this, take the partial of this function here with respect to y. Okay, so in the first case, you treat x as a constant, and then in the second time, you treat y as a constant, or vice versa. You notice if you did the other way around here, if you did f sub y, and then took the partial derivative after that with respect to x, you get exactly the same thing, okay? So that will always be the case for everything we cover in this course, okay? Any other questions? Okay, let's go on to a slightly more interesting example. So I mentioned at the start that the reason we care about many of these things in a biological context is that we say want to maximize or minimize some quantity, okay? From an evolutionary perspective, you might want to maximize fitness. From an agricultural perspective, like in this question here, we might want to maximize the yield of a crop when we're putting in different types of nutrients. So this model here, the yield Y of an agricultural crop is a function of the nitrogen level N and the phosphorus level P in the soil. So they're measured in whatever units they happen to be here. We're not going to worry about the units in this particular question. So we've got this function here, which is saying, okay, as we vary the nitrogen, as we vary the phosphorus, the yield of our crop will vary. K is some positive constant. We don't need to worry about exactly what it is now. We can leave our answers in terms of K. The question is then, what levels of nitrogen and phosphorus result in the best yield? So you're a farmer and you want to produce the most crop you can. How do we work this out? Okay, this is exactly the same type of problem that we've just done. We want to find our critical points of this function. And then from that point, work out whether those critical points are maxima or minima, okay? So have a go, first of all, at finding the critical points. Again, I'll wander around and see how everyone's getting on, okay? If you find the critical points, you can carry on and classify them if you want to, don't wait for me. In fact, because time's short, I'm going to give you a little head start here. So the partial derivatives, y sub n, is going to be k times by p times by 1 minus n e to the minus n minus p. And through symmetry, we get yp is kn times by 1 minus p e to the minus n minus p. So I'll give you a little head start there. So those are the partial derivatives. You're going to find your critical points by setting those equal to 0 at the same time and solving them, okay? Have a show of hands. Has anyone been able to find the critical points yet? 3, okay. So if you haven't found them, if you're stuck at this point, know that k is constant and is positive. So when we set these equal to 0, the k's, we can cancel them out. E to the minus n minus p are exponential. This is always going to be positive as well, okay? So we can just divide through by those when we set these partials equal to 0. So we just have p times by 1 minus n is equal to 0, and n times by 1 minus p is equal to 0 as well. Okay, so can anyone tell me what, from these two equations here, what these two equations, what our critical points are going to be? So when you say 1 and 0, then you mean n is equal to 1, p is equal to 0? So if n is equal to 1 and p is equal to 0, then this will be equal to 0. But if n is equal to 1 and p is equal to 0, then this will be equal to 1. So we need to solve both of these equations simultaneously. So if, for example, in the first case, this first equation here tells me that p must equal 0 or n must equal 1. So if we take the case where p is equal to 0 in this equation, and then substitute p is equal to 0 here, then we're going to have 1 minus 0 in the brackets. So that's 1. That tells me that n, have I got this around the wrong way? Let me just check. No, this is fine. I thought I'd written something down wrong there. We end up with 0, 0 and 1, 1. Okay, so either n and p must both be equal to 0, or n and p must both be equal to 1. Okay, so have a go now at classifying these. So work out your y sub nn, y sub pp, y sub np, and then your discriminant. And then use that to identify the maximum yield for this crop. Okay, there's only 3 minutes left, so I'll just go through the answers here. So y sub nn turns out to be kp times by n minus 2 e to the minus n minus p. And we have kn times by p minus 2 times by e to the minus np. It's nice that things are symmetric here. And then ynp is k times by 1 minus n, 1 minus p, e to the minus n minus p. Okay, so if we then substitute these into our discriminant at 0, 0, we have, so this is at 0, 0, d of 0, 0 is going to be just equal to, well, because we've got a p here and an n here, the ynn and ypp are both going to be equal to 0. And this term here is going to be positive. So we're going to be taking away something positive minus something, whatever it is, squared. That's fine. So this is going to be negative. So that tells me that this is a saddle point. And then at 1, 1, we're going to have this term here is going to be equal to 0. And then we are multiplying something that is negative. So this n minus 2, when we substitute n is equal to 1, this is going to be negative. And likewise, we're going to have something negative here. Negative times a negative is going to be a positive. So we're going to have our d at 1, 1. It's going to be positive. And then we've just worked out that yn is negative at 1, 1. So what does that give me? What's the classification for that critical point? D is positive, and the second partial here is negative. So if we go back to our table, or in this case here, we have a local maximum. Okay, so it tells me that we achieve the maximum yield when n is 1 and p is 1. We can work out what that maximum yield is by just substituting this function value, this point, back into our function here. So y at 1, 1 is going to be equal to, let's see, we're going to have k times by 1 times by e to the minus 2. Okay, so whatever units this happen to be in, this would be our maximum yield. Okay, so in a question like this, if you ask what's the maximum yield and when does it occur, well, you find the point at which it occurs, and then substitute it back in to actually find what the maximum yield is. Okay, that's it for today. Thanks, everyone. See you on Friday.